Thank you and good morning, and thank you everyone for being here today in this virtual field day. I'm a graduate student at the University of California, Riverside, working with Dr. Amir Hagwardi. My study is focused to optimize water use in landscape ground covers. In this presentation, I will highlight the effect of varying rates of deficit irrigation on landscape ground covers and show you some preliminary results from the ongoing research. By the end of this presentation, I hope to share you the importance of irrigation zoning in landscape irrigation and show you some ground cover species which are growing well regardless of the irrigation treatments. Landscape plants are thirsty. Landscape ground covers are ornamental, low-growing shrubs or perennial plants, which forms a continuous soil covering. Irrigation of landscape ground covers in arid region uses significant amounts of water. About 50% of residential water is used for landscape irrigation, and in United States alone, landscape irrigation uses 9 billion gallons of water every single day. That is 9 billion gallons of water. That is a lot of water. The reasons of water loss are different. The reasons of water loss in landscapes are over-irrigation, improper irrigation management, and inefficient irrigation systems or methods. About 50% of water we use outdoors is wasted because of inefficient watering methods and systems. But these are some fixable issues which can be taken into consideration during irrigation planning. To reduce water use by landscape, irrigation should be based on plant species and the ability to meet the plant water requirement while minimizing over-irrigation. However, there are few studies so far that evaluated the effect of irrigation treatments on ground cover species or which identified the actual water requirements of the ground covers. In our research, we are trying to identify the effect of deficit irrigation on 12 different ground cover species. We are also evaluating the health and aesthetic beauty of these ground cover species using cutting-edge sensor technologies. We are doing this ground cover study at the Agricultural Experiment Station in Riverside. The picture in the background is the experimental site where we are currently doing this research. I have a short video to play. In this video, I'm giving you a 360-degree view of the experimental field. We have 12 different ground covers and 4 different irrigation treatments replicated 3 times in randomized complete block design. In total, we have 144 plots. Each plot is of 10 feet by 10 feet dimension. Each plots are irrigated using 4 quarter circle pop-up heads controlled independently using solenoid valve. Plants were planted in early 2019. They were under full irrigation for the first year of establishment. Once they established, we imposed different deficit irrigation treatments starting May 2020. I hope you enjoyed the video. As mentioned earlier, we are using 12 different landscape ground covers in this research, some of which are shown in the moving picture on the right. 4 different irrigation treatments are 20% of reference evapotranspiration, 40% of reference evapotranspiration, 60% of reference evapotranspiration, and 80% of reference evapotranspiration. To irrigate the plots, we are using autonomous smart irrigation controllers, and Dr. Hagvardi has described in details about its working principle and the irrigation, the evapotranspiration-based irrigation treatments. To evaluate the growth and health of ground covers, we are collecting ground and aerial data using various sensors twice a month. We have green seeker to measure the normalized difference vegetation index, also called.
Reminder for everybody to mute themselves. Okay, Anish, you're, I think you got muted, but you're back. We can hear you, and everybody's background is muted now.
Okay, did I miss anything? I'm in this slide.
Yes, you're on this slide, yes.
Yeah, you're
Okay.
good, sorry.
Okay, so I'll begin again. So to evaluate the growth and health of the ground covers, we are collecting ground and aerial based data using various sensors twice a month. We have a green seeker to measure normalized difference vegetation index, also called NDVI, which is a good indicator of plant physiologic growth. NDVI has a strong correlation with green coverage, above ground biomass, and plant vigor. We are also using canopy temperature. We are also measuring canopy temperature using the infrared sensor. It will tell us how stressed the plants are. In addition to this, we are flying DJI Matrix 100 drone with multispectral MicaSense Redis camera and FLIR DuPro R thermal camera to evaluate the aerial images and their potential in studying the physiological characteristics of landscape ground covers. Picture in the center is the aerial photo taken using the drone. It shows the field layout with 144 plots and is showing the normalized difference vegetation index match for each of those 144 plots. Water stress in plants affects physiologic growth. To quantify the effect of water stress, we are also measuring stomatal conductance and leaf area index. Stomatal conductance is the measure of carbon dioxide entering and water vapor exiting out of the stomata of a leaf, and it is an indicator of plant water status. In water-stressed plants, stomatal conductance value will be low. Leaf area index, on the other hand, is another important measure affected by water stress. It evaluates plant growth and canopy. In this graph, I'm showing you the water use by different irrigation treatments between May and July from the beginning of this research after we imposed the deficit irrigation in May. In x-axis, we have date. In y-axis, we have cumulative irrigation applied in inches. The 4 different irrigation treatments are represented by 4 different color bands. The 2080 uses less water, little more than 5 inches, while the 80% evapotranspiration treatments uses more water, more than 20 inches during the same period of time. Given this huge difference in the water use by 4 different irrigation treatments, you might be wondering, can we grow our ground covers using less water while maintaining the aesthetic quality? The answer to this question will come in next few slides.
Anish, if you let me just add something quickly to the previous slide. So basically, this is a good point to tell you how we actually, as a practical point, how we actually schedule irrigation this ET, 20% ET, 40%, 60%, and 80%, we are imposing these using a smart evapotranspiration controller. So the controller estimates reference evapotranspiration by itself. We tell the controller for this particular plots or groups of plants or zones, just apply 20% of the reference evapotranspiration, okay? So in reality, if you know that some of your ground covers and niche fields show you that need only 20%, then the only thing that you need to do is for that particular zone, dial 20%, and then that would be 20% of the reference ET. Okay, Anish, you can continue.
Thank you. This slide is little busy here. Please bear with me. I'm presenting here the normalized difference vegetation index values and NDVI values obtained using the handheld sensor that we measure using the green sticker. In this graph, we have irrigation, 4 different irrigation treatments in the x-axis, plant species in the y-axis, and scale on the right represents the NDVI values. The greener is the better, as it represents the plant's green coverage, vigor, and strength. I will not go through all the species, but I want you to focus on some of these. Let's first see the ice plant in the blue dotted box. The NDVI values for ice plant are almost same for all 4 irrigation treatments. The values ranges between 0.7 to 0.4. This shows that the effect of irrigation water was not significant. Even with applying 20 ET treatment, we are getting same quality compared to 80 ET irrigation. Let us see another species, lantana, in this black dotted box. The NDVI values seems a little different in this case. The 2080 treatments, the NDVI value is leaning towards red, meaning less coverage and greenness of plant, while applying less water, but it increased with increasing water rates, increasing irrigation water. So what we can say, like, it shows that plants will have different water requirements from one species to another. In the coming few slides, I'll show like how these 4 different irrigation treatments looks like. Let us first see the ice plant. I have 4 different canopy pictures from 4 different irrigation treatment. On the top left is the 80% of evapotranspiration, and on the bottom right is the 20% of evapotranspiration. So what we see here is, regardless of all these 4 irrigation treatments, the canopy coverage, greenness, and the growth of plants is almost same. So this implies that for this specific plant, we may irrigate less water and get the same aesthetic quality. But here, the effect of irrigation was significant. This is lantana. Lantana seems to be sensitive to drought and requires more water to grow well. The quality and growth of this lantana increased with increase in irrigation water application, which we can see in the picture here. So again, we have a lantana with 80% of evapotranspiration on the top left. It is growing healthily and is flowering well. While we compare this to our 20% evapotranspiration on the bottom right, the 20% canopy is very less. They are dried, and it almost seems like we are losing the plant. So the effect of irrigation in lantana is significant. Like lantana might be sensitive to drought, and it might need more water compared to the ice plant that I presented earlier. Another species which grew well regardless of the amount of irrigation water application is creeping Australian saltbush. It also has same vigor and quality for all 4 irrigation treatments. Uh, Dr. Morhart had raised some interest in the canopy temperature in his earlier slides. Canopy temperature tells us whether our plants are water stressed or not. In this graph, we have again the irrigation rates in the x-axis, plant spaces in the y-axis. The scale on the right is the temperature in Celsius, but the corresponding temperature in Fahrenheit is presented in the orange column. Blue means cool, while red means the hot temperature. Higher canopy temperature greatly impacts the quality and growth of the plants. I just wanted to compare how it looks like. The picture that just popped in is the NDVI values that I presented earlier, where the greener is better. So what we can say is higher the canopy temperature, lower the NDVI value. Again, the NDVI value is red. The red is corresponding to red. The red is corresponding to red. So with increase in canopy temperature, it's like we are losing the health and growth or the quality of the plants. And the other thing we want to notice is in some species like Australian saltbush, the canopy temperature is relatively low or cool, regardless of the irrigation treatment. So we still want to study further and determine whether some of these species like Australian saltbush, coatables, they might have some potential of reducing the inland temperature.
Can I interject 1 second on
Sure.
that slide? Because that's one thing that was important. The buckwheat temperature is high, but it's going dormant. So yeah, it may lose color, but it's its survival mechanism. So that's what they would normally do. So I think that's something that's going to be understood as we study these plants. Some of the other ones, like the ice plant, it's curious to see how well they're going to tolerate the drying. Like the jasmine is a high temperature too, and there may be leaf burn as it gets older and established, but we'll see that as the months go by. But a high temperature is necessarily not indicative of the plant's survivability. It may be its mechanism of surviving through drought. So we got to be careful that we don't get the two confused. Does that make sense to everybody? Hopefully it does.
Thank you. Coming into leaf area index, in general, the leaf area index increased with increase in irrigation rates. In the given picture, for all four pictures, we have four different irrigation in the x-axis and the leaf area index values in the y-axis. In some species like coatables, regardless of the irrigation treatments, the leaf area index or the canopy remains significantly same. But suppose for lantana, the leaf area index for 20% evapotranspiration irrigation is lowest, while the 80% evapotranspiration is the highest. If you remember those four pictures of lantana that I showed earlier, 80% evapotranspiration had green canopy, while the 20% evapotranspiration was very dry. Another physiological characteristics, the stomatal conductance that we measured also had some effect. So I want to focus on some species like lantana again. The lantana in x-axis, we have irrigation treatments. In y-axis, we have stomatal conductance. The species I'm talking right now is lantana with solid circle and dark black-like line. So for 2080 treatment, the stomatal conductance is lowest, while for the 8080 irrigation treatments, the stomatal conductance is the highest. And we can see in the picture above, for 2080, they are again dry, and the 8080, they are growing healthily. So it shows like the stomatal conductance also helps us to determine the growth and the health of those landscape ground covers with respect to the irrigation treatments. You might be wondering, we have orange line over here that seems to be relatively straight with reference to the irrigation rates. That is because, so the orange line is creeping Australian saltbush. For all 4 plants, there was not the significant effect of irrigation. They had like similar canopy growth and the health. So the stomatal conductance was significantly same for all the 4 irrigation treatments. So we recently started this research with post irrigation treatments from the May 2020. But so far, what we know is different plants have a different water requirements. So if we have a different plant species in our landscape, different ground covers, then we may consider dividing them into different irrigation zones. Some species like ice plant, creeping Australian bush, Saltio evening primos, coyote bush might grow well even in deficit irrigation, but further study is still in progress to strengthen our results. Remote sensing technologies like handheld or drone-equipped sensor can help us to detect water stress in the plants. With this, thank you, and I'm happy to answer any question if you have, and if not, I'll try to get back to you soon.
Thank you, Anish. That was great. So since we are running behind, I recommend that we switch to Ninder's presentation so he can also present, and then we collect any question that audience